Hello. Hi, everyone. Welcome to our seminar series. I am Kazi. I'm going to be moderating today's seminar, subbing for John, who is currently sick. So today it's a one-woman operation. So today I would like to welcome our great seminar speaker, Dr. Schoeberl. Is that correct? Thank you. Who is going to talk to us about the Hunga-Tonga Ha'apai eruption. So Ralph, our associate director, will introduce him.
Yeah, I just want to welcome Mark. He's going to speak today. It's probably a very interesting topic. So Mark's chief scientist at Science and Technology Corporation, STC. And he specializes in stratospheric processes. Mark, previous career, a very distinguished career at NASA Goddard, was chief scientist of the Aura and was it project scientist for the EOS Aura mission. He's got a bunch of awards and recognitions in professional societies, and he's a Midwesterner, right? Got from Iowa, but he's got his degrees, from you are from Iowa, but he got his degrees at Iowa State and his PhD at Illinois. So I think I'm going to turn it over to Mark. So thank you for coming.
You're welcome. Okay, so I not mess up the slide system, and I hope to provide you with a tsunami of information, which will erupt from the speaker's podium, and hopefully it won't be a pyroclastic event and other dad jokes. Okay. So this is the opening thing shows the eruption cloud. It's a little movie I was playing, and I'm not sure how to get it to start again. Click on it. Say, here we go. Yeah, so you can see the eruption here. These are my co-authors here. Yi Wang at STC, Rei Uyama at NASA Ames, Augustin Taha at NASA Goddard, Andy Dessler at Texas A&M, Wanda Yu at Hampton University, and Eric Jensen at Ceres. Okay, so let's see, page down. So this is an overview of the talk. I'm going to give you details of the eruption in the short time after this thing blew up. And then I'm going to talk about changes in the stratospheric constituents and the temperature after the eruption. And then some information about cross-equatorial transport of the plume and Hunga-Tonga's impact on climate. I'm going to summarize everything. This is a tremendous natural experiment. This eruption went, as I'm going to show, it went up into the mesosphere, produced a lot of stuff up there, and then it got transported around. And it's really great that we have an observing system to see all that stuff. I'm going to show mostly from the microwave limb sounder and the OMPS limb profiler, which is on NOAA 21, I think. And they provided a tremendous amount of information on the stratospheric trace gases and aerosols. That's what we're going to look at, and we're going to use this what most of the talk's going to be about. So this is the some details of the eruption. It erupted on January 15th. 4 people died from tsunamis. The eruption generated tsunamis across the Pacific Basin. It was a submarine volcano and a magmatic water explosion called a Surtsean-Plinian type eruption. Surtsea is an island off of Iceland. That was the first time they saw a volcano erupt and an island emerged, the island of Surtsea. And Plinian is referring to Pliny the Elder, who documented the eruption of Vesuvius during Roman times. This magmatic water explosion is consistent with the high amounts of water vapor, although most eruptions do produce a lot of water vapor in the stratosphere if they get that high. So water vapor and SO2 are the main plume constituents. It was the most explosive observed event since Pinatubo in 1991. It's part of the subduction zone, which is shown up here. There's a subduction zone here, and Hunga-Tonga's here. Fiji's underneath this thing here. American Samoa is up in here, but this is the Australian plate. And then this is the Pacific plate, and there's a subduction zone. New Zealand's North Island is also very volcanic and part of that structure. So you can see down here a lamb wave propagating away from the volcano, and it goes water vapor. And you can see that the explosion was heard in Alaska, believe it or not. This shows the island before and after on the bottom here. See, this is before and this is after. You can see the eruption pretty much decimated the island. So here's some more eruption information. The peak eruption height was 55 to 57 kilometers based on stereo and shadow use. Here's a shadow example of the eruption cloud. This is Carr in 2022 and Proud in 2022 also documented this height. They agreed on the height. And then it went from 55 to 28 kilometers in about 10 hours. So it went way up and then it sort of collapsed back down. You can see these dots here show the altitudes, 60 kilometers at the top. The dots are the maximum peak. And then you can see the IR and visible altitude from nadir pointing systems. So this is the plume collapse. It's quite rapid. So lightning rings were observed in the plume. This is pretty interesting. You can see the rings. So go forward here. You can see the rings forming from the eruption cloud. These blue dots are the lightning strikes, and you can see them propagating away from the cloud. And it's associated with the gravity waves. It's like a up-down motion away from the cloud. If you throw a rock into the pond, you get the ripples. The upward motion, downward motion, the convection associated with that gravity wave or the strong displacement created the lightning rings. These are Australian soundings. The cloud, after erupted, moved to the west and it went over Australia. And these are water vapor soundings. And I don't know if you can see this, but there's up to 1,000 parts per million. For those of you who don't study the stratosphere, the number we keep in our heads is 4 for the amount of water vapor in the stratosphere, 4 parts per million. So 1,000 is like, oh my God. So these are Australian water. And it actually, they had some problems with calibration. The numbers were so large. So a little more about the eruption. So let's do a little historical perspective. So this Krakatau was the biggest eruption since Hunga-Tonga, the previous eruption. And it erupted at 30 to 40 kilometers. There's a very nice paper by Hamilton and Sakazaki, 2017, documenting what was observed in the tropics associated with Krakatau. It was a magmatic eruption. It produced a lot more SO2, they think, based on the sunsets and visible sunset information. So Hunga-Tonga released only about half a teragram. A teragram is 1 metric ton. So about half a teragram of SO2 based on the data from Karn et al. Using UV measurements. Here's the SO2 cloud here. And this is the SO2 column out in Dobson units. And Pinatubo's up in here, and here's Krakatau in the or Krakatau sometimes it's pronounced. But there's been a recent paper by Soletto in 2023 analyzing the IASI data, and he suggested that maybe we were closer to 1 teragram, about double the amount that the SO2. And it may have been because the clouds blocked some of the eruption clouds blocked some of the UV backscatter, and so we didn't get to see all the SO2, whereas the IR measurements do a better job. And here's the decay of SO2 with time. So there seemed to be a rapid conversion of SO2 to sulfate aerosols with an e-folding time of about 6 days initially, and it's this little downward dent here. That's from Karn. And then there's a longer e-folding time, about 17 days by Soletto. And this is still pretty fast. After Pinatubo erupted, they kind of come with this canonical number of 30 days for a decay time. And this is 17 days. So it's still pretty fast. Why did that happen? Well, the extra water likely increased OH, which is used to convert SO2 into H2SO4 through a number of reactions. And so Zhu pointed this out, or Zhu simulated this process in a Nature paper. Okay, so let's look at the aerosol measurements. So the sulfur dioxide goes up into the cloud and it's converted to sulfate aerosols, basically a sulfuric acid droplet, and it grabs water molecules around it and forms an aerosol. This reflects the sunlight back, and it can be seen with the OMS limb sounder, OMS LP. So the aerosol optical depth is what we use to measure the amount of aerosols. And they're obviously closely related to the SO2 emissions. So the lower the HT has lower SO2, it means the AOD will be much smaller than, say, Pinatubo. The OMS LP AOD was increased in mid-April. This is a graph from OMS LIM data. This is the AOD at 550 nanometers. And you can see the growth. Here's the eruption. There's a growth up till about mid-April, and then there's a decay after that. And this is the global average. Now, the reason I compute the global average, even though most of the aerosols in the southern hemisphere, is when we talk about volcanoes and starting to compare them, everybody in climate business uses the global average. So we're kind of want to be on the same page. The aerosols are mostly confined to the southern hemisphere. So this is from Taha 2022. You can see the aerosol amounts here, and you can see this is March 22nd. And there's some stuff coming out here along the side, and that's very typical of the lower stratosphere, where you have transport by waves and storms that penetrate into the lower stratosphere and move stuff along isentropic surfaces, potential temperature surfaces, this is potential temperature, these numbers. And this shows a 30 south to 10 north aerosol extinction to molecular ratio from Taha. And you can see there's conversion of SO2 to aerosols in this period after the eruption, 15 to 20 days. And then it sort of sits there. But then you can sort of see, I drew a line here, this white line here, it's very thin. You can see it descending with time. And that's settling of the aerosol field. So the aerosol droplets, they're not like a gas, they have gravitational settling. And yet people put that into the models using Stokes parameters, et cetera, to model the settling process. So now I'm going to switch to the water vapor plume. This shows January 17th, shows the water vapor from MLS. The microwave limb sounder was the one that provided most useful data on the water vapor plume. It's a limb sounding measurement, so it gets a little long track north to south. It's in sun synchronous orbit, about 1:30 crossing time. It's on Aura. And so the location of the tracks are about 25 degrees longitude apart. So it's not going to get a perfect picture of the plume, but it does hit the plume occasionally at the beginning right in here. And you can see the structure of the water vapor field moving all the way up here. So normally, as I said, 4 to 5 parts per million in the stratosphere, 26 kilometers. Now, this is a little movie of the plume. You'll see it go. And I averaging 3 days together here, and you can see the plume go as it slides over Australia to the west. And then it sort of smooths out. This is into March. The dates are on the top. They're kind of hard to read. But you can see it zonalized, so to speak. This is all at about 25 kilometers up. The temperature field is on the black contours. So initially it was kind of lumpy. Obviously it's eruption, so it's one spot, then it breaks up, but then it smooths out into the zonal field. Okay. So this is, I'll move on just a couple days here. I'm going to show you a movie this a little bit later, but just gives you some experience in looking at these. So this is the temperature field. It's the white dots. Hunga-Tonga is here. This is the equator in the middle, and this is the original plume you just saw in the last slide. So by January 30th, the lower part of the plume has disappeared. You can see here, I put a black line as a reference here. You can see that it's right above the black line. Now it's way above the black line. And you see that also that the plume has moved across the equator. Here it's just sitting on one side, move across the equator, which is extremely interesting to me. My background is in atmospheric dynamics. Like, why did that happen? That shouldn't have happened. And then you see the plume moves equatorward. Now, the reason the water vapor content gets bigger is that the better sampling from MLS. Very simple. And then we get this equatorward movement of the center of the plume a little bit. Up at the top here, there's a lot of water, but then we have this poleward transport that's going on, which is across equatorial circulation that occurs in the upper stratosphere. And so there's a nice paper by Wandi Yu talking about the mesospheric circulation here. Okay, so what's the total water vapor? A participant has, can you see that on the, is that thing on the top there? Okay, I can exit. Okay, thank you. So this is the total amount of water above 100 hectopascals, and see the big jump here. This is again in teragrams. So we're over 100 teragrams of water in the stratosphere, and that's about 10% of this total stratospheric water if you integrate it over the whole globe. And if you think about that for a second, one eruption at one little location in the South Pacific increased the total stratospheric water by 10% all by itself. It's sort of amazing. And then you can see it jumps up and then it decays a little bit. And there's another little thing here, which I don't quite understand, but I've tried to deseasonalize this. To compare, this is Pinatubo. Pinatubo didn't go very as high as Hunga-Tonga, and you can see the water vapor went up and dropped right back down. This is a simulation by Abdelek Hader. I probably mangled his name, which is kind of nice to show us a comparison. And but there was water injected by Pinatubo, but not nearly as much as Hunga-Tonga. And there's some uncertainty as the water vapor amount. MLS version 5 gives you 127. MLS version 4 gives you 146, which is what the MLS people prefer we use. Sage 3 gives 113, and ACE FTS is 137. But we're all about 120 or so teragrams. So that's probably not an unreasonable number. And I mentioned about Pinatubo already. So let's go on to. Yep. We'll go forward. What happened? Oh, there it goes. Okay. So now let's look at the aerosols and water together. So here's the aerosol field, and here's the water field. So this is February 1st. This thing at the corner here is polar stratospheric clouds, which also are observed as in the aerosol field. And then we see the plume, the aerosol plume stuck up here. And this is height. I just got to put the altitudes on there. They're kind of hard to read. So this goes from 15 to 40 kilometers, which is most of my plots do. There's water vapor. Then you see about April, you see the extension across the equator here for water vapor, and you see the extension across the equator for aerosols. But then about April, you start to see this push even further across the equator, expansion. Then there's this expansion sort of blobs itself out. The aerosols are sinking. You can see I'll compare this one with this one, and they're moving downward as a function of time. Water vapor continues across the equator here and spreads out by July in these different directions. Still pretty much confined to the southern hemisphere, however. So let's look at some other trace gases. This is from a really nice paper by Michel Santee, who's on the MLS team. So to look at this, see, this is a time series. This is 2018 to 2022 at 24 to 26 kilometers. So the scalloped looking regions here are the edge of the polar vortex. That means that this is where the Antarctic ozone hole forms in these regions down here, and the Arctic ozone hole forms in the regions up here. So the important point is that here's the eruption, this little green volcano thing, and you see the water vapor. Gotta go back. Water vapor from MLS, and you can see that it's excluded from the vortex edge. So the 2022 ozone hole was formed and isolated before the water vapor really got to that point. So it didn't have anything to do with 2022. But let's look at some other things here. So you do see some evidence of chemical processing. This is chlorine monoxide, and chlorine monoxide is showing elevated levels here downstream, and it's associated with the aerosols and heterogeneous reactions on those aerosols. And likewise, you see a depletion of HCl. You see the blue here. This is the depletion of HCl. And likewise, you see a change in nitric acid. So nitric acid here is sequestering NOx. NOx is sequestered by all the water. And by sequestering it into nitric acid, that also allows for more chlorine monoxide to exist without being locked up into chlorine nitrate. Now, what about ozone loss? So you see these heterogeneous reactions. Well, ozone is increasing. So what? Well, that makes no sense. You've got all these things that destroy ozone, and ozone's increasing. Well, this is the problem during this period, is the QBO is descending. So the QBO actually has a descending circulation. I'm going to show a little more about that. And it pulls the ozone down from the ozone peak. And that's what's going on at these altitudes. You're getting the ozone increasing at this region. So this is a kind of a complicated to determine if there's any ozone loss. So what about the 2023 Antarctic ozone hole? Okay, so 2022, that's a nothing burger. 2023, maybe interesting. So this is MLS water vapor on 5/29/23, end of May, and here's in the beginning of June, and this is 10 days later. So look at the big change that's gone on here at the South Pole. So you can see this big dehydration event gone on, and do we see ice? And the answer is yes. This is before the Calypso mission died. You can see this is from their quick look. You can see ice has formed. This is their track here across Antarctica. You can see ice has formed here. And this is about 2 weeks earlier than normal from the climatology by Pitts in 2018. So we're seeing early ice formation. And this slide, oops, let me go back. This got turned sideways. And I don't know how that happened, but if you manage to turn it the right way, not sure what's happening here. You see this red line? The red line here is actually showing that there's early ozone loss in the 2023 ozone hole in June and July. There's June and July over here. So I'm sorry about this slide. Why it turned sideways occasionally happens, but we have to deal with it. The blue is the previous year, 2022, and you don't see anything like that. So there's something interesting going on here. Okay. Next slide. So stratospheric temperature changes. Okay, so water vapor is a strong long-wave IR emitter, as everybody who deals with the Earth's atmosphere knows. If it's very humid at night, it doesn't get as cold. That's actually due to dew point issues, but I digress. This is a long IR emitter, and increases in water should trigger cooling. So do we see its temperature change? And the answer is yes. So this is the water vapor at 15 south, and this is the heating rate anomaly at 15 south, which cooling is in the blue here. So we expect to see some strong cooling going on in this thing. These calculations were using the AAR radiative transfer model. And then the temperature anomaly shows up, and you can see that the temperature anomaly shows up in about the same spot. It's a little different. It's not perfectly co-located because you're going to trigger some dynamical response, and it's going to be not quite perfectly co-located with the temperature. This is from Vomel et al. 2022, which is a really nice paper in Science. This shows the water vapor field, and this shows his plots of the temperature change from climatology. And you can see, again, you see cooling right in the same spot we see, and a little bit of warming down low here. And in fact, there is a little warming. It's kind of buried under this slide here, but this arrow, but there's a little bit of warming in the lower parts here. So I wanted to show you a little bit of what you see with in the case of the temperature and circulation response from the Goddard 2D model by Eric Fleming. This is a paper that's being revised now. It's been submitted, and there's revisions in 2023. The 2D model, the advantage of the 2D model is it has a full chemistry package, and it's very fast to run, and it uses residual circulations, et cetera, but it generates its own circulation. And it also has the QBO in it, and the QBO looks exactly like the QBO that's reserved in reanalysis fields. So this is the water vapor. They injected the water vapor, and then this is the temperature response. Now, this is kind of a funny color scale. You can see the blues are really out to -3, and the reds are only to 1. So I put the numbers in here. This is about 0.7 and -3. So there's big, strong temperature response. And in the previous slide, the -3 is about what we got as well on the previous slide. And then this is the circulation that he's computed just from the Hunga-Tonga water vapor field. And you see this cooling here. It produces a sinking motion, which sets up this secondary circulation here. And then there's some rising here. And then there's also the heating down below produces the opposite direction. You get this kind of motion toward the pole. Now, I have to tell you that these circulations are really weak. They're not as strong as the normal stratospheric circulation. So these are perturbations on top of the regular stratospheric circulation. Okay, so just to give you a summary so far, After the initial explosion to 55 kilometers, the rapid plume collapsed to 30 or so, below 30. High amounts of water vapor, low amounts of SO2. The aerosol cloud rapidly formed shortly after the eruption. Not much ozone loss, but heterogeneous chemistry was evident. HT water vapor stayed out of the 2022 ozone hole, but was present in 2023. Possible early Antarctic ozone loss in 2023, which looks like it's going to be a pretty low year. According to the NASA Ozone Watch, which you should go look at if you want to keep track of the ozone hole. Aerosol and water plumes are mostly confined to the southern hemisphere. Aerosol is slowly settling out and the water vapor is kind of spreading in multiple directions. Okay, so as I said earlier when I started my talk, this is a really great natural experiment. So we can look at how the Hunga-Tonga plume evolved, and everything I've shown you so far except for the 2D model was just observations. So how did the plume evolve, and how do we how have the models simulated what we're looking at, or what new understanding can we get from the plume? So I'm going to first look at the distribution of constituents and the transport circulation. I'm computing the transport circulation from MERA2, but I'm correcting the heating rates that are in MERA2 because MERA2 doesn't assimilate water vapor in the stratosphere. It just uses a fixed value. And why not? The last 50 years, it's always been about the same until you get a volcano. And then there's also aerosols. So you've got MERA2 doesn't quite have the right heating and cooling. And this is in McCoy et al., although they try with their updates of the temperature field to get as close as they can. But I've corrected this transfer circulation from MERA2 and for the additional water vapor. And then I'm going to use a trajectory model to simulate the plume motion using those corrected winds and corrected heating rates and see what we get. Okay, so this is what I'm going to show you. It's a little movie. And in this movie, you're going to see this white line here is a zero wind line. And so this is the descending QBO westerlies here. So they're sitting at the beginning here. This is at January 1st, 2022. The date is up here. And this is the location, dotted line's location of Hunga-Tonga. And then the equator is this thick, solid white line here. Over here, you're seeing, again, the zero wind line, the easterlies and westerlies, and you're seeing the circulation as these black contours. This is basically the residual circulation. Okay, so here you go. And guess what happened? Boom, there's the volcano. And you can see the water vapor, the aerosol spreading out across the equator almost instantly. And the water vapor plume is starting to move out. And you see the westerlies descending here, right here, as a QBO. And it looks like it's sort of splitting the water vapor in half as it descends out. And then the water vapor relaxes a little bit. And then it goes down and it seems to sort of split the aerosol distribution in half as it descends. And then the water vapor spreading. Okay, we lost OMS LP for a little bit. It's back. And then the water vapor is now spreading upward into the upper stratosphere with the Brewer-Dobson circulation. And it's also descending into the higher latitude region. So this is, we're already into November, and I think the movie ends in December, the end of December here. And you can see the water vapor is pretty spread out now at this point. And the occasional polar stratospheric clouds. It's starting up again. No, it goes on and on and on. So we're down into 2023. I forgot how far this went. You can see the water vapors all through the region, all spread on this side. And it's all completely dry now in here. Sort of amazing. Okay, I'm going to go to the next slide. So this is now going to be the trajectory calculation. So what I did was I put a big pile of parcels in here, about 163,000 parcels in this domain, which roughly models the region of the initial launch, and they're just put in over the Hunga-Tonga location. Okay, and then I'm going to show you the particle density as a function of time after the eruption. And I'm going to put water vapor, MLS water vapors over here so you can get an idea of how good we do with the trajectory calculation. So here we go. And you'll see that there's the eruption. And you can see the trajectory calculation going on over the left. and it's spreading out. Now remember, water vapor is not going to be in the lower stratosphere because it's so cold. It's pulled out, but you can see the spread of the trajectories. Now the interesting part is, do you see many trajectories going into the northern hemisphere? No, they're not going there. They're stuck in the southern hemisphere, except very low down, about 20 kilometers, you see them. When the QBO descends, you saw a little bit of trajectories moving into the northern hemisphere, but mostly not. And it's going to repeat, and you can see it again, that everything in the trajectory calculation is stuck in the southern hemisphere. And this is using corrected mirror to winds. So one of the things that we haven't done well is we haven't figured out why this water vapor got all the way into the northern hemisphere almost right away. What the hell happened? So that's very interesting from a dynamics viewpoint, because that's a transport problem. Okay. So there are actually two events. One is the first event, within the first 20 days, water vapor is in the other hemisphere. The second is something that happens in mid-April, which is the QBO descent, where you see this bulging of the water vapor out into the northern hemisphere. So this is going to I'm going to rerun this movie showing the water vapor at 26 kilometers. I'm going to look at the streamlines, which are shown here. See the streamlines? Those are white. Those are from Mira 2. And you can see they're very, very zonal along the equator. They're just moving directly to the west. Okay. So let's see if this will start. Okay. Might be able to just shift. Okay. There you go. So you're going to see the eruption, and it starts heading off. I changed the scale slightly on the water vapor, but boom, it's already across the equator. And the flow vectors are not sending stuff in that direction. So it's not following the streamlines from Mira 2. It's doing its own thing. Okay, so why did that happen? So what might be going on is that we've forced a Gill mode. And Gill wrote a paper about Rossby waves in the tropics and how they can be forced by heating. And this is an example, is this figure here. So what you get is a Rossby mode, which crosses the equator, and you get flow that goes from one side of the equator to the other in these Rossby. Now, it isn't a Kelvin mode. The Kelvin mode only has flow east-west. It has to be a Rossby mode or mixed Rossby gravity wave. But the point is that these Gill modes can be forced. And so my hypothesis is that the strong radiative forcing associated with the cloud, both the water vapor and aerosols, is forcing a Gill mode. Remember, the cloud is very localized at the initial part, and it will force these kinds of modes in the equator, and they have cross-equatorial flow. So let's look at the wave numbers. This is kind of hard to read, but this is pre-eruption. The wave numbers at the bottom here, latitude is on the side, it goes from minus 40 to 20. Pre-eruption, there aren't very many waves in the tropics. There's just a little bitty wave 2. And then here's the eruption. This is by January 20th. You see the strong wave 1, and it intensifies. Even wave 2, it starts to appear as the thing stretches out. And then you get both wave 1 and 2, and then they fade away. So this is by the end of January. So this is pretty consistent with the wave modes being forced by radiative transfer processes, both heating and cooling of aerosols in the lower stratosphere. So that would explain why things are pushed across the equator. So what about the QBO transport? This is from ANSTI in 2022. It's kind of a hard diagram to look at. The QBO is sort of centered in the middle here. Here's the Brewer-Dobson circulation. This is descending westerly, so it's nice of him to pick that for us. And then there's a circulation around it. And that's more easy to see from the originator of this circulation, Plume and Bell in 1982. They're the first ones that showed that the descending westerly phase would produce a circulation like this. Okay, so you've got this descending part right in the middle, and then you've got this spread at the bottom, and then a re-spread backwards at the top. Okay, this is really symmetric around the equator in the idealized Plume and Bell simulations, but as shown early in the late 1990s, you can actually move some PV around, and then it'll be a little bit less symmetric. So you can get some cross-equatorial flow by the QBO during that if you move some PV around. So let's look and see what we see. And I pointed to it earlier. So here's the water and aerosols are already across the equator as of March 1st. So this is the picture, and here's the aerosols, and here's the water. And again, the white line is the zero wind line. Okay. So now the QBO is descending. This is the white line starting to descend. You can see there's a little teeny dent going on the top of this distribution. And as it descends further, you can see it's pushing the distribution apart, just as we expect. And then it goes further down. I don't know if you can see the white wind, it's down to this point now, the white line, and it's starting to push the aerosol distribution apart. And now the water vapor is actually coming together again. So you're getting a QBO repair, so to speak, as a secondary circulation pushes them back again. And then you're getting aerosol pushed back together in the QBO repair. So this is really interesting because the QBO is really a barrier to cross equatorial transport at these altitudes. Higher up, you get stuff going back and forth all the time. But at these altitudes, it's really preventing stuff from moving back and forth. But this is really kind of cool. Shows what kind of nerd I am. I think that's cool. Anyway, so summary of the plume transport. So you have the Gill force Rossby mode, which likely pushed some of the constituents across the equator right after the eruption. The descending QBO circulation further splits the aerosol and water vapor fields across the equator. And as the QBO shear zone descends further, the split is slightly repaired by the reverse circulation above the QBO zone. So that's sort of a summary of the transfer. Now, in these reanalysis fields, for example, MERA2, they do have a very good QBO. That's not the issue. But the issue apparently was this Gill force mode. And again, this is a radiative transfer problem where all these aerosols and water are hanging around the stratosphere, and they're make assumptions about what water and aerosols are up there, and they're not right. And so they don't get the Gill mode either, which is why my trajectory calculation didn't do a good job. Okay, so now I'm going to go to the last part of this talk, which is climate impact. So large volcanic eruptions have had a measurable impact on climate due to sulfate aerosols reflecting sunlight. So Pinatubo in 1991, well, it was originally thought it was about 0.5 degree centigrade cooling of the surface, but Fujiwara in 2020 corrected that, saying that they included some El Nino effects, and so the number should be about 0.15. Now, I might say that there's a Crutzen paper in 2016 where he suggested we throw aerosols into the stratosphere and create, geoengineer the stratosphere so we can continue to burn fossil fuels and not worry about carbon, because the stratosphere aerosols will cool the climate. And that's launched an enormous engineering industry on why can't we do that. There's some guy in Southern California putting SO2 in little tiny balloons and sending them up in the stratosphere. I don't think he understands the units behind what's required to produce even a 0.5 degree centigrade. We're talking about 100 megatons of SO2 to do that. And a little balloon is probably 2 or 3 ounces of SO2. Anyway, so basic math would get you that you really need to put a lot of SO2 up here. There's 2 other problems with geoengineering that I can think of right off the top of my head. One is when you produce aerosols, you can see that we produce some heterogeneous chemistry. So there could be ozone loss, unintended consequence kind of crap. The second thing is the lifetime in the stratosphere is only 2 or 3 years. You throw it up there, 2 or 3 years later, you got to do it all over again. And that's way beyond a presidential budget cycle. So that's never not going to happen again. Okay. So I digress. Krakatau in 1883 cooled the atmosphere about 1.5 to 1 degree, they think. Again, it was a long time ago, and it's harder to figure that out. And in Tambora in 1815 was even bigger. It was a VEI 6 or 7, and maybe about 1 degree. This is very uncertain, but it is recorded that it was the year without a summer. They had frost in New England in June. It was very, very, very cold, and it may have caused the French Revolution, some people say. Anyway, not directly. So changes in stratospheric water vapor also influence the climate. There's a really famous paper by Susan Solomon in 2010, and a follow-up paper by Andy Dessler talking about how if you increase the stratospheric water vapor, you're basically going to change the climate. And so for example, in Solomon's paper, there was a drop in total stratospheric water in around the year 2000 to 2008. And she calculated that that actually reduced the surface IR flux into the troposphere because water vapor is radiating the IR, and that caused some cooling, which disguised global warming. And there's another paper, and Desser's paper in 2013 quantified that the effective water vapor is about 0.27 watts per meter squared per ppmv in the lower stratosphere. And of course, if it's more water, it heats, and if it's less water, it cools. So Hunga-Tonga produced more water than is usually produced by a volcanic eruption, but we have a competing process. It produced less aerosols. So we have less aerosols and more water. So that's kind of interesting. And just to reiterate the issues here, in the visible and shortwave infrared is where we're talking about the aerosols affecting things. Also, I might add that the water vapor has an absorption band in the shortwave. And so water vapor will also cool the climate a little bit, but the IR part is much bigger. I might add also that you got to think about clouds. Clouds reflect a lot of sunlight back into space, so you got to correct for cloud stuff. So most of these climate calculations that are done in the back of the envelope climate calculations are done, they neglect the effect of clouds. The more modern ones do include cloud effects. So in the long wave infrared, you have the temperature, water vapor layer, you have cooling the space, you have a little bit of a temperature decrease, you have a temperature increase down below where there's the cold tropopause, and you have IR flux convergence, and then you have the increased heating in the troposphere. This is, again, Susan Solomon's kernel function for water vapor only, and this is the short wave part here, this dotted line, and the long wave part is this dashed line here, and then they use dynamical corrections to get the net here, and this is in watts per square meter. So we've computed the AOD using the OMS LP observations. I've shown you that. So the AOD changes the surface solar forcing, delta I, and we developed a parameterization for delta I based on different volcanic eruptions. We also can use the parameterization developed by Yu and Wang in 2023. They use MERA2 data, which has an aerosol, tropospheric aerosol package in it, and they use the aerosol package to calculate what the climate effect would be. And it's a very nice parameterization because they have not only clear skies where there's no clouds, but they also include a cloudy sky thing. And there's less surface effect, obviously, if there's clouds, and you can see that in here. The blue is the strongest effect, and the green is almost zero. So the amount of clouds also reduce the amount of radiation hitting the surface. So this is watts per meter squared per AOD here. So we're going to look at both these, the Yu and Huang parameterization as well as our own. So this is what we came up with. So most studies parameterize the effect of the surface radiation as minus R times AOD. So R is some number that they use. Comes from different places. So Hansen in 2002 came up with an R value of 21. We get about 19.5 from our fit. So these are all the volcanoes here. And then this is linear fits are these curvy lines, because this is a log plot here. And then there's a straight line, which actually intersects most of the volcanoes. So I might say that, you know, we have about 20 teragrams of SO2 from Pinatubo, and here's Hunga-Tonga down here with its little pathetic, I should say pathetic, about one teragram. And I'm sure Hunga-Tonga is insulted by what I said. Anyway, there's a Chichon and Agno and everything. So our number we get is about 19.5 from a linear fit, but the log fit is actually better. And that's this black line here. And this is the equation for the log fit, which we're going to use in a second. Yu and Huang is abbreviated as YH. So what you're looking at here is a time series of AOD from the OMS LP instrument. And you can see that AOD doesn't get really big. It's, you know, it's like 0.05. It's not really big. You wouldn't really notice much. But using the log fit equation, you get this value for the change in forcing. So we're talking about maybe 1.5 watts per meter squared change in solar forcing. in the peak here. This is YH parameterization, and they actually look pretty good. They agree pretty well. And so it agrees with log fit. And then this is YH parameterization with including clouds. And you can see it knocks it down by about half when you include clouds. So a lot of these calculations that have been done in the past with these AOD values and estimating climate change have forgotten about clouds being important. So that's something that a lot of climate models need to make sure they've done right. Okay, so what about the IR flux due to water vapor? So again, we're going to use the AER RTM, Malwar et al. We're going to change the SWIR flux is only changes are only a function of the water vapor concentration, the shortwave infrared fluxes. But the long wave fluxes also can change because of trace gases or temperature changes in the stratosphere. So this gets to be kind of complicated, and we got Hunga-Tonga altering both temperatures and water vapor concentration, maybe a little teeny bit of ozone, another IR important IR gas, and N2O, not much. But anyway, this creates a problem because we got all these different cases, and the combined impact is kind of noisy. So I'm just going to show you the impact of the water vapor anomaly only using the climatology of temperature. So what I'm taking is the temperature climatology from MLS, and I'm adding the water vapor perturbation associated with Hunga-Tonga to it, and I'm looking at the change in the downward IR flux. This is the simplest. Okay. So here's the change in the IR flux. This is water vapor at 25 kilometers. This is the long wave flux into the tropopause. This is right at the tropopause. This is the short wave flux. This is cooling. There's a change in scale here. And this is the change in flux warming. So the net change is a slight warming. You get that as a function of time. So there is some slight warming, a small change in the downward flux at the tropopause. So it's, maybe 0.25. Okay, so what's the bottom line? Long wave flux, short wave IR flux from water vapor, and then the aerosol direct forcing. Well, the aerosols win. Even though the aerosols weren't a lot in this eruption, the aerosols win. And there's net cooling going on here. So you get, with clear skies, you get about minus 1.1 watts per meter squared. It's the maximum here. And for cloudy skies, you get about 0.44. Again, it knocks it down by about half. So the forcing is negative. It will cool the climate. So Hunga-Tonga is not going to warm up the climate. That's an important point because there have been a number of papers that have already been published that didn't consider the aerosol forcing, that said, we're going to die because Hunga-Tonga is going to create a huge amount of IR flux that's going to radiate us all like we're in a broiler oven. And then that got picked up by some people on the far right and said, oh, this warm summer we've had is all due to Hunga-Tonga. Well, the water vapor is not overhead during the summer, or isn't much there. The impact is tiny, and second, the aerosols are changing things. They're more powerful. Okay. So how long will the water vapor anomaly last? This is again from the 2D model, which does a pretty good job of lifetimes. You can check it using, say, SF6. Juan Hall published a really nice paper on summarizing how we know about how long stuff lives in the stratosphere. It never lives longer than 5 years at the most. So here's the water vapor anomaly. This is a function of latitude and time at I think it's at 25 kilometers or 26 kilometers. And you can see it initially, we're sort of in here somewhere. And it's pretty much doing what it shows here. The water vapor, and this is the mid-stratospheric cooling associated with the water vapor, and there's a little bit of warming down low, but then it switches over to cooling. But the lifetime is about 2.5 years. So that's what we think will happen with the water vapor according to the 2D models. And of course, the climate models are going to have to weigh in on that too. Okay, so I'm going to summarize. Hunga-Tonga produced about a 10% increase in total stratospheric water. There's a persistent water vapor layer 20 to 30 kilometers. This is due to the height of the plume, which got above the cold lower stratosphere. The cold lower stratosphere causes a lot of the ice to fly out of the stratosphere, condenses ice. That's why Pinatubo didn't have as much water, because it didn't produce as much, but also didn't go as high. SO2 is about 10 times smaller than Pinatubo. So AOD was also about 10 times smaller than Pinatubo. The constituents are mostly confined to the southern hemisphere during the first year. They spread out a little more at high latitudes into the northern hemisphere in the second year. There's some evidence of heterogeneous aerosol processing in the MLS data from the high chlorine monoxide values and loss of HCl, which is the reservoir gas. Mid-latitude ozone loss appears to be minor or buried by the QBO changes. H2 Hunga-Tonga water vapor aerosol layer did not affect the 2022 ozone hole, but it may have increased ozone loss in 2023. That's we're still in the middle of that ozone hole, so we don't know yet, but it may happen. Transport using the reanalysis winds failed to simulate the cross-equatorial crossing at the beginning of the eruption. It's probably because there's a forced gill mode, a Rossby mode that was generated. I forgot to mention that the gill modes will propagate with the disturbance. And in fact, if you look at the phase propagation of those waves that I showed you, they propagate with the disturbance. The second event of equatorial crossing appeared to be associated with the QBO descent. At least it isolated the water vapor and the aerosols. Climate, Hunga-Tonga climate, a water vapor layer heats the troposphere as far as the climate impact, but the aerosol layer cools the troposphere, and the cooling is bigger than the heating. If you scale the observed atmospheric cooling, just the aerosol part, to Pinatubo, the Hunga-Tonga temperature decrease would be less than 0.04 degrees. And I defy you to find that in the meteorological data. It'll be really hard to see. Anyway, so these are some of the references I used in the talk. But there's a tsunami of papers being written about this event, as I said earlier. They've erupted in the literature. Some of these are in ESOR already and out there. And I'd like to acknowledge my co-authors and some NASA funding and STC for encouraging me to do this, and my colleagues at NASA and NOAA. This is a nice painting by John Shin Zhu, who was one of the zoo paper I referenced earlier. She did that. And that's about it. Thank you. A lot of material.
Anyway, any interesting questions before we move to online?
That was a great talk. Question: any of the satellite products you use also used in the reanalyses, or are they dependent?
Well, yes and no. So the water vapor from MLS is not used in the reanalyses. That's the problem, part of the problem. Aerosols, I think to some extent, the tropospheric aerosols may be used. I don't not exactly sure about the answer to that. I know that they Mera-2 produces an aerosol product partly from the go-kart, which I think has some ingestion of observations. There's air pollution, so there's aerosols in the troposphere all the time, and they want to make sure they get that part. So, but for the stratospheric, mostly what they ingest is temperatures, and they use GPSRO temperatures in the stratosphere, and then above, I think, 50 kilometers, they use MLS temperatures. The GPSRO kind of peters out around 40 kilometers or so in quality. But the biggest issue, again, is the lack of water vapor in the reanalysis field. So I tried to correct for that. Obviously, I didn't correct for the gill mode forcing, or didn't generate that either. But we grow, we learn. And MLS is probably going to go offline in a couple of years, and so as Aura re-enters, so I don't see there's any motivation to start including it now.
Okay, no, thanks.
I could do Sage, I guess. That's still around.